Today I'll be going over the notes for targets 8 and 9. Targets 8 and 9, you did learn in Algebra 1 the properties of exponents. So we will go through them here, but please make sure if you have any further questions, if you don't remember what we are talking about, that you come in and see your teacher. So the first page on here of Target 8 is just the properties that you need to know about exponents, properties that you learned back in Algebra 1, and hopefully we remember some of them. So we need to remember when terms have the same base. So when we talk about bases today, we're always talking about the number or the variable that has the exponent on it. So when you have the same base and you're multiplying those bases, our rule for that is you're always going to be adding the exponents. So it'd be a to the m plus n. We add those exponents together. So we have a couple examples here in 1 and in 2. I'm actually going to start with 2 because I think that's the easier, simpler problem we have. So I have the same base of 2 and 2. So we're multiplying those bases together. That means I'm going to add those exponents. 3 plus 4 is 7. When I look at 1, I'm doing the same exact thing. The only thing is I have multiple variables here and I have some numbers. So we're always going to multiply the like variables or the numbers by each other. So let's start with my numbers. I have 3 times 5. We know 3 times 5 is 15. Then I have y squared, and I also have y. Remember, this y has a first power on it. We just don't put a first power on every single number that we write. So y squared times y to the first, I add those two exponents, and 2 plus 1 is 3. Then I have z to the fourth and z. Again, z has an exponent of 1 on it, so that gives me z to the fifth. And last but not least, I have an x and I have an x squared. The x has a 1 on it, so I have x cubed. When you see answers, you're usually going to see them written in alphabetical order. So I would have 15 x cubed, y cubed, z to the fifth power. For 3 and 4, our next rule is if you are dividing. Again, when we're dividing here, notice that we have the same base of a. So if you have the same base and you're dividing, we're going to take those exponents and we're going to subtract them. Okay, so if I look at number 3 here, I have r cubed over r to the sixth. I have the same base, so I'm going to subtract those exponents and I get -3. So I would have r to the -3. Looking at number 4, we are going to do this again, but we want to make sure here, since we have different variables, that we match the variables up. So I have h to the fifth and I have h. Remember, that's to the first. So I'm going to subtract 5 minus 1 and I get h to the fourth. For the second thing, I have j squared and j to the 10th. 2 minus 10 gives me -8. Last but not least, I have k and k to the sixth. Remember, that's k to the first over k to the sixth. 1 minus 6 is -5. What we're going to learn in the next one, though, is negative exponents we never want to have in our answers. So our answers to 3 and 4, whereas they're not wrong, they're not correctly written because we always want to get rid of those negative exponents. So if you have a negative exponent, if you have an a to the -n, we're going to rewrite that as 1 over a to the +n. So when you have a negative exponent, you're always going to flip the side of the fraction it's on and make it positive. So if you were to have, let's say, 3 over 2 to the -2, -2 can't be in your answer, so we're going to move that up top with our 3. So I would have 3 times 2 squared. The 3 didn't move to the bottom because the 3 didn't have a negative exponent on it. You only move what has the negative exponent on it. So if I look at number 5 down here, I have x, and then it's to that -3rd power. So I'm going to move that x to the +3rd power down in the bottom of the fraction. We have to have a placeholder up top, so we put 1. So if I go back and I look at 3, 3 would really become 1 over r to the positive third power. Let's go look at 4 now, and then we'll go down to 6. If I look at 4, the only thing that's wrong in here is I have a negative on the j and I have a negative on the k. That h to the fourth is going to stay in the numerator. It has a positive exponent. The j has to move down. When I move it down, the exponent becomes positive, so I have j to the eighth. The k has to move down, so when I move the k down, that also becomes positive, and I have k to the fifth. That would be your final answer because you have all positive exponents on it. If I look at number 6, the only thing that has the negative exponent on it is that v to the negative third. So my t squared and my q are going to stay up. They're not the same base, so I can't combine them, and I'm going to have that v to the third in the denominator. The next rule is the zero power rule. The zero power rule is one of the easiest rules to use. Anything to the zero power is 1. So if I give you z to the 0, that's just 1. So when I look at number 8, I don't have anything to the 0 power yet, but let's start simplifying. We're going to use a couple of the rules we already used. So first thing I want to do is I'm going to multiply my numbers together. So 4 times 2, I get 8. X to the fourth times x to the negative fourth. We add those exponents together. 4 plus a negative 4 is 0, so I get x to the 0 power. I have y squared and y to the negative 2. 2 plus negative 2 is 0, so I have y to the 0 power. I have z. I don't think I have another z here, so remember those both have a power of 1 on them. We add those, so we have z squared. We're not done yet because we can still simplify. I know x to the 0 is just 1, so it's going to be 8 times 1. Y to the 0 is just 1, so times 1 again. Well, 8 times 1 is just 8, so my final answer is 8z squared. The next property we have is for distributing an exponent. So you're going to notice that these exponents are outside of the parentheses, and I have two bases inside. I have a base of a and I have a base of b. We have to distribute this exponent to both the a and the b. A and b both have an exponent of 1, so when I multiply 1 times m, I get a to the m. B has an exponent of 1. 1 times m is b to the m. So you'll distribute that exponent to everything inside the parentheses. Same thing goes with division. I'm going to have to distribute my exponent to the numerator, and I have to distribute my exponent to the denominator. So I have a to the m over b to the m. So let's practice that. So in number 9, I have 3 different bases inside. That just means I have to distribute this exponent 3 different times. So I have q squared, r squared, s squared. Over when I do division, I have to distribute that negative 3 to everything inside. So I have x to the negative third, y to the negative third, over z to the negative third. But I have negative exponents there, so I need to flip them. The x to the negative third moves to the denominator, becomes x to the third. Y also has a negative exponent, so we have to move it down. And then the z has a negative exponent, so we have to move it up. Make sure when you switch sides of the fraction that that exponent becomes positive. Our last property here is a power to a power. When you have a power to a power, you want to multiply those exponents together. So a to the m times n. So on number 11, I'm going to multiply my 4 and 2. So I have x to the 8th. On 12, I have to distribute that power to everything, and we have to multiply them together. So when I do that, I'm going to have 3 to the 4th. Remember that 3 has an exponent of 1 on it. M to the negative third becomes m to the negative 12th. N squared becomes n to the 8th, multiplying those powers together. We'll move that m to the 12th to the denominator to make it have a positive exponent. And that's our final answer. When we go to the back, we're just going to continue practicing these, but we're going to have multiple of them in every problem. So we might use the power to a power and our multiplication or our division rules all in one. When you do these, don't stress so much on where to start. Do whatever you see you can do first. Sometimes there's going to be several options for that. When I look at this first problem, I notice up top in my numerator, I can simplify some stuff. I can multiply m squared by m squared. I'm multiplying with the same base, so I add my exponent, so I get m to the 4th. I have n squared times n to the negative 1. Again, I'm multiplying with the same base, so I can add the exponents, and I get n to the 1st. In my denominator, I'm going to keep that 4 down there. Then I see m to the negative 4th. Well, I know if it has a negative exponent, I'm going to have to move it to the top. So I'm going to go ahead and I'm going to move that m to the 4th up top. I have that n to the negative 2nd on the bottom, but again, it has a negative exponent. So I'm going to move that n squared up top. So now I'm going to have to simplify again. In my numerator, I have m to the 4th times m to the 4th. I add those exponents because I'm multiplying those bases. I get m to the 8th. N to the 1st and n squared gives me n cubed, all over 4. In B, I see I have the power of a product property because I have these exponents on the outside. Remember, when you have the exponent on the outside, you're going to distribute that in to every exponent in there, every base you have. So I have y to the negative 4th. I have x to the negative 16th. And the second parenthesis, we have to do the same thing, distributing that 4. So I have x to the 4th. I have y to the negative 12th. Now, right here, it's up to you. You can decide to move your negatives to the bottom. You can decide to multiply those together. I'm going to move my negatives to the bottom this time, so I have x to the 4th up top. It had that positive exponent. Down to the bottom, I'm moving my y to the 4th, my x to the 16th, and my y to the 12th. Now in the bottom, I have multiplication. I have y to the 4th and y to the 12th. So I'm going to add those exponents together, and I'm going to get y to the 16th. Now I also have x to the 4th and x to the 16th. Remember, with division, we subtract, so I'm going to do 4 minus 16. That gives me negative 12. So right now I would have x to the negative 12th in my numerator. When you subtract, it always ends up in your numerator. But I know I can't have that negative exponent, so I'm going to have to move that to my denominator as well. So I have x to the 12th, I have y to the 16th, all in my denominator. I have to have something in my numerator, so I put a 1 up top. In C, first thing I'm going to do is just like B, I'm going to distribute that exponent through. So I'm going to distribute 3, the 4, and the 2. So I have a to the 12th, b to the 6th. In the denominator, 2 has an exponent of 1 on it, so I'm going to keep it down there. I have a to the negative 2, so I'm going to move that up top to get a squared, and I'm going to keep b squared in my denominator. One more step of simplifying. I have a to the 12th and a squared. We're multiplying in the top, so I have a to the 14th. I have b to the 6th and b squared. It's division, so we subtract. 6 minus 2 is 4. So I have b to the 4th. Remember, that always ends up in the numerator. And then I have this 2 in my denominator, so it's all over 2. D, we're going to do the same thing again with distributing our exponent. So when I distribute it up top, I have u cubed v to the 4th times 2 to the negative 3rd, u to the negative 3rd, v to the negative 12th. all over 2vu squared. Okay, pick one thing to start with. So for me, I'm going to pick the top. I'm going to simplify everything I can. So in the top, I have u cubed and I have u to the negative third. When I add those exponents, 3 minus 3, I get 0. Well, I know u to the 0 is 1, so those are going to be gone. I have v to the fourth and v to the negative 12th. When I add those together, I get v to the negative 8th. I have 2 to the negative third, so I'm going to move that 2 to the negative third to the bottom, so I have 2 to the third. In my bottom, I still have times 2 vu squared. Okay, that v up top has a negative exponent, so I know I'm going to have to move it down to the bottom. So I'm going to have that v to the 8th in the bottom. When I simplify, you can't have your numerator blank, so I'm going to have a 1 in there. I have 2 cubed times 2, so I have the same base, so I'm going to add those exponents, and I have 2 to the 4th, or you can put 16, whatever you prefer. I have v to the first times v to the 8th, so I have v to the 9th, and I have u squared. Okay. There are lots of properties here that you need to learn. The only way you're going to learn them is through practice. So please work on your homework, go through these. If you need more, get the extra practice online. You can do them, it's just learning all of those properties you have to. The last thing we're going to do here is we are going to simplify radicals. You did this back in geometry. With numbers, we will start adding variables. So we're going to do this by making our factor trees. So remember, factor trees, we want to break down 72 into 2 factors. I would always recommend looking for something that multiplies to 72 that is a perfect square, since our goal here is to take the square root of it. So I know 72 is 2 times 36. Both of those would still be underneath the square root because you've taken the square root of nothing. When I look at that, though, I know the square root of 36 is 6. So when I take the square root, that number comes out. 2 is not a perfect square, and I can't break 2 down in a factor tree. So my final answer is going to be 6 square roots of 2. Okay, so 200. Well, I'm going to break down 200 so that I can get a perfect square. I know 100 is a perfect square, so I'm going to split this into 100 and 2. I know the square root of 100 is 10, so I can pull that out. We have to be careful on this one because we have a 3 on the outside. Whatever you pull out, you're always going to multiply it by the number on the outside. So that leaves me with 30. 2 I can't split up, and it's not a perfect square, so I end with 30 root 2. Okay. So remember, while you're doing this, it might help to write out your perfect squares. So I know 1 square is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25, 6 squared is 36, 7 squared is 49, 8 squared is 64, 9 squared is 81, 10 squared is 100. We can keep going. Let's go up to 12. So 11 squared is 121, and 12 squared is 144. So when I talk about breaking the perfect squares, I'm trying to get it to be like these numbers on the right because I know I can take the square root of them. So when I look down here at C, I notice that I have a variable in there. When I think about C, I think about it as the square root of 48, and I think about it as the square root of x cubed. So I kind of split it up into 2 different problems. So square root of 48, breaking that up, I'm looking for one of my perfect squares. I want to look for the biggest one I possibly can. So I know 16 will go in there. So 16 and 3. The square root of 16 is 4. So I have 4 root 3. But I can't forget about this x cubed over here. There are several ways to think about this. I always look for groupings of 2 because I know for a square root, if I have a grouping of 2, I know the square root of x squared is x. So when I have x cubed, I know x cubed is x squared times x. So the square root of x squared is x, and I'm left over with x underneath. So when I combine these, I multiply my numbers on the outside of the square root, so I have 4x. I multiply the numbers inside the square root, so I have the square root of 3x. And that would be your simplified form. Another way of approaching the square root of x cubed, I know the square root really means there's a 2 out here. I'm not taking a cube root like we did with the graphing the other day, but I'm taking a square root. I think of how many times does 2 go into 3. I know 2 goes into 3 one time, so I can bring 1x out because that means there's one grouping of 2x's in there. When I take 2 out, I'm left with 1 underneath, so I'd have x to the first underneath. So let's look at D, our last problem from the notes today. I am looking at the square root of 68, the square root of x cubed, the square root of y, and the square root of z to the 5th. So square root of 68, let's start by breaking it down. Okay. Now, let's do this one. You don't know a perfect square that goes in there, so maybe you wanted to divide it by 2. So we can do 2 and 34. Well, I can't split up 2 any further. 34 is not a perfect square, so I'm going to split up 34. So 34 is 17 and 2. We can't split up 17 any further because it is a prime number, so I'm stuck at this point. So if you get here, you're always looking for pairs. So since I have 2 square roots of 2, remember square root of 2 times square root of 2 is square root of 4, and we know the square root of 4 is equal to 2. So anytime you have a pair of square roots, you're able to take that number underneath out because technically you have a perfect square. So I'm going to have 2 on the outside now, so I have 2. This square root of 17 I can't break up any further, so I'm going to have the square root of 17 left. So right now for my answer, I have 2 on the outside, and I have 17 on the inside. So I'm going to do it like I did this second way here and think of a 2 on the outside here. Okay. So if I'm looking at my x cubed, I'm thinking how many times does 2 go into that 3? Well, 2 goes into 3 one time, so I can bring 1x out. I'd have 1x left over. Y has an exponent of 1. Well, I can't divide 1 by 2, so 2 does not go into 1. So I'm going to keep my y underneath. Then I'm going to say 2 goes into 5. 2 goes into 5 two times. So I have a z squared I can pull on the outside. And then I'm going to have 1 left over. So I have 1z left over underneath. Again, sometimes these can be hard to get started, hard to look at. Please come in for help. There are several ways we can go about this process. So if this doesn't make sense to you, please come in and we can go over a different way to approach the problem.